Hey guys, so in this video I'm going to introduce satellite motion and circular orbits. Let's check it out. So a satellite is any object that orbits another. So if you have two objects are orbiting each other, for example the moon going around the earth and the earth going around the sun, these are usually obviously for astronomical objects, then the satellite is the one that is orbiting the middle object. So for example, the object in the middle, we're going to call that big M, and the object around it little m, and that's because the object that's orbiting is the lighter one. So if the moon goes around the earth, the moon is little m and the earth is the thing in the middle, so it's big M. If the earth is going around the sun, so the earth is little m and the sun is big M, because again the sun's in the middle. Okay, now there are different types of satellite motion, or different types of satellite orbits. You might have an elliptical orbit, or you might have a circular orbit, and the one we're going to focus on in this video is circular orbits. Okay, so it's important for you to know that the way you're going to get an elliptical orbit or a circular orbit depends on the initial velocity of the satellite. So it says here, for a satellite launched from the Earth, its orbit, or really for any planet, right? So it doesn't have to be just the Earth. Its orbit, which is the shape of its path, there's like a bunch of different shapes here, we'll get there in a second, depends on its initial speed. You can also call this launch speed. Depending how fast you throw something, it might take a different shape. Okay, so let's check this out. I made this sort of a velocity line here to show you how this works. So first of all, imagine that there is a cannon up here, and it's pretty far up somehow. They built a massive cannon. This is sort of a thought experiment, and it's a classic thought experiment in physics to help explain this. But if you put a cannon here and you shoot, well, first of all, if you don't shoot it at all, there's no velocity, right? So nothing happens. But if you shoot it, it's going to move. Now, if you shoot it with a little bit of velocity, it's going to sort of just fall and hit the earth with velocities, with paths A or B. And that's just projectile motion, horizontal projectile motion. We've done that. So you get projectile motion A and B. All right, so that's nothing new. The part that gets weird is if you shoot this thing fast enough, it's going to have a circular orbit around the Earth, and it basically never touches the ground. And that's because as it's falling towards the center of the Earth also sort of curves beneath it, so it just keeps looping forever. And that's in fact exactly how satellites work. To get satellites around the Earth, we sort of fly them out here, and then we push them out with a certain velocity, now obviously a very precise velocity, so that the satellite will then keep spinning. And that's because the satellite has an initial velocity this way, but the Earth is pulling it that way, so it just keeps doing this, right, in circular motion. Uniform circular motion, in fact. Okay? So there's a magic speed at which if you were to throw something, you would get a circular orbit. And that's this, I'm going to call this V circular. Okay? At this exact number, you would get circular. So let's say this number is 5,000. Okay, just making that up, 5,000 meters per second. That means that if you throw something with 4,000 meters per second, it's going to go really far, but it's going to eventually land and hit the Earth, right? And obviously this is assuming that there's no buildings on the way, it's not killing anyone, right? So it's a theoretical situation, but it wouldn't make the full circle. If you throw something with 5, it would make an exact circle around the Earth. So if you throw it from 1 meter, eventually go all around the Earth and come back to you at 1 meter and just keep doing that. It would be weird to see. If you throw it more than 5,000, let's say 6,000, then it's going to have an elliptical orbit. So circular orbit is C over here in the diagram. Elliptical order is D. Okay? Elliptical order means it's sort of a distorted circle. So instead of a circle, let's say that's a circle, it would look kind of like this. Okay? So, but we're not going to get into that now. And also, there is such a thing as a speed that's so fast that the object loses, that the object escapes the Earth. It's too fast. The Earth can't pull on the object hard enough to keep it in a circle, and the object escapes the Earth. So let's say, again, I'm just making this up. I'm going to scratch these out later. Let's say this is 10,000. So if I throw something between 5 and 10, I get elliptical. So it's a big range. If I throw it faster than 10, it escapes the Earth and never comes back. All right, let me scratch these out because these are not the actual numbers for the Earth, and I don't want you guys to get confused there. So anyway, that's the setup of what might happen depending on how fast you throw something. And we're going to see this, and for some of you guys, you're going to get into this as well. All right, so circular orbits are simpler. That's why we're going to focus on circular orbits, okay? Because they have a constant path, all right? Now, planets have elliptical orbits, right? But what we're going to do is we're going to simplify by saying that they're circular enough, or nearly circular. When you see the words nearly circular, it just means you're going to consider it to be circular, okay? So we're going to simplify planetary motion so that we can use more simple physics. And like I said, for some of you, we might get into elliptical orbits later, and you'll see how that works. So in circular orbits, the orbital speed, which is how fast you're going, and the height, which is h, this is height, are related by this equation right here. Now let me quickly show you how to get to this equation, because it's actually pretty easy. So let's pretend this is a satellite or you or whatever. So you would be moving this way at that point with a v-tan, tangential velocity, because you're going around a circle, so it's off the circle, right? Which I can also call v-sats, because you're basically behaving like a satellite now. Okay, and you would also have an acceleration towards the center, AC. By the way, when you're over here, you would have v this way and a this way, okay? This is just uniform circular motion in such a way that you're forming, obviously, a circular path around this planet. So let's say this is the Earth, okay? So I want to write an equation that shows you what the velocity, a relationship for the velocity. So you might remember velocity in uniform circular motion problems, we can find either using AC equals v squared over r, or F equals ma. So I'm going to do this. I'm going to write sum of all forces in the centripetal direction equals mac. Now, the only force here acting on you is the force of gravity. Okay, the force of gravity is pulling you in. So I'm going to put here force of gravity equals m, and then I'm going to replace AC with v squared over r, so we can get this number. Now, the force of gravity is given by this equation here, right? Universal law of gravitation, big G, big M, little m over r squared equals mv squared over r. I want to remind you, big G is the universal gravitational constant right here. Big M would be this mass. Little m would be the satellite. R is the distance between the center of both. So R is actually this distance right here, from the center of the Earth to you. Little r is a distance, not necessarily a radius, and sometimes they're going to be different things. Okay? Notice that this distance, little r over here, is made up of two things. I'm sorry, I meant to call this little h over here. This is a height, okay? Little r is a combination of your height plus the radius of the Earth. So hopefully you see that. It's the radius of the Earth plus how far away from the Earth you are. So I'm going to write here the little r is the radius of the Earth plus your height. And I want to remind you that little r is distance from the center, which isn't always the radius, right? And this is height, and obviously r is the radius of the planet. So in physics, uppercase letters are used to mean a constant. They signify that this is a constant. Like big M, the mass of the Earth, not changing. Radius of the Earth, not changing. Big G, universal constant, never changes, right? Now R and H change. You could move farther, which would increase your H, therefore would increase your R. Okay, cool. So let's finish this up real quick. We're almost done. I can notice that this little m cancels with this little m, and this r cancels with one of these. So now I can just solve for v and show you that v equals the square root of big G, big M over r. And that's what I'm going to put right here. That's the first equation we have for satellite motion, that the speed of a satellite, or that the velocity of the satellite, has magnitude of the square root of gm over little r. Notice that it's little r, not big R, so it's not the radius of the planet, but it's the orbital radius. That's what that's called. This is called orbital radius, which is the distance not from the surface, but from the center of the planet. Orbital radius or orbital distance is another way you can see that. Okay, so this is also, notice that this is the mass of the Earth, not the mass of the object. In fact, right here, there's a little point that says, notice how a satellite's motion does not depend on its own mass, little m. It only depends on the mass of the thing in the middle, right? The planet or the star that it's rotating around. So I get this equation, and if I combine this equation right here with this equation here from uniform circular motion, I can solve for t. T will equal, if you move stuff around, 2 pi little r over v. So v is 2 pi r over t, so t is 2 pi r over v. Now, if you do this, and I get v sat, which is this guy here, and I stick v sat right here, okay, I'm going to end up with this really, really ugly equation. Okay, let's write that. This is going to be 2 pi r to the 3 over 2 divided by the square root of gm. Now, some books, some professors don't actually give you this equation, and you only get as far as having to find a period using this. But to find a period of a satellite, which means how long it takes to make a full rotation around whatever planet or star it's rotating around, you can use either one of these equations. Obviously, to use the smaller one, you have to already know v. To use the big one, you don't have to have v. So this is more straightforward, but it's also more messy. Okay? So those are basically the 3 equations you would have, and you need to know at least these 2. For some of you, you're going to have to know all 3 of them. Okay? So an important point here is this. For every height a satellite may have, there's an exact corresponding speed it must have to maintain that height. Okay? If I want a satellite to be in a circular orbit at 2 kilometers above the Earth, there's a very specific velocity it needs to be in. If it's slower, it's not going to work. It's not going to stay in that exact height. If it's higher, it's not going to work. So you might imagine that this is a very precise thing because you put satellites in space and you don't want them to just go away and get lost and you lose all your investment, right? So that's pretty interesting. And I can show you that here. R is a constant, right? R is a constant. So the only variables I have is h and little r, okay? Actually, let me just write it this way. V equals the square root of gm over little r. The square root of gm, I can replace little r with r plus h. And I can show you that everything here is a constant. The only thing that's not a constant is h. So the idea is that as h changes, v changes, and there's a one-to-one mapping between the two, meaning if one changes, the other one has an exact corresponding number. The same exact thing happens for t-sat. Notice how t-sat changes. Everything here is a constant except r, and inside of r, the only thing that's a constant that's a variable is h. Okay, so those 3 things are related. Okay, orbital speed v, period t, and height h are interdependent. They're interdependent. All right. I can also show you how they are going to affect each other in terms of, if this grows, what happens to that. So as height increases, as a satellite gets farther and farther from the planet, if you want to have your satellite farther from the planet, your velocity will decrease. And I can show you that here really simply. If my h increases over here, then r obviously increases. And this is in the denominator, which means this will decrease. Your period, if you look in the period equation, if your h increases, your period increases. So it's the opposite. And this should make sense because decreasing means you're slower. So your period will be greater, which means you're slower, right? Greater period takes longer, so you are slower. All right? So the closer you get to the Earth, the faster a satellite has to be. And that should make some sense because if you think about it, the satellite, if it's not super fast, it's going to fall into the Earth. So if you get closer, it's getting pulled harder and it's closer. So you have to be moving faster to be able to continuously not fall into the earth and keep sort of not escaping but staying at that same constant rate. Anyway, long story short, we got these three equations here. Let's do a problem real quick. So here it says the International Space Station, ISS, is in a nearly circular orbit. Nearly circular just means we're going to treat this as circular orbit at 370 kilometers above the Earth. So you have to know your equations, but you also have to know your variables. Which variable is 370 above the Earth? It's your h. That's your height above the surface of the Earth. 370 kilometers or 370,000 meters. Calculate its orbital speed. So A, calculate its orbital speed. Orbital speed is given by the square root of gm over r. Notice you don't have r yet, right? So r is big R plus h, and I have these numbers. Big R is the radius of the Earth, which I have up here for you guys. It's 6.37 times 10 to the 6. So 6.37 times 10 to the 6 plus h, which is 370,000. And when you add this, you get 6.74 times 10 to the 6. Okay. What really sucks about this stuff is that this topic is going to have a lot of big numbers again. All the gravitational topics, you're going to have a lot of big numbers. Cool. So that's my r, and I can now plug it in here. So I can now find my v. V is the square root of g. G is 6.67 times 10 to the negative 11 with a bunch of units. And m is the mass of the Earth, 597 times 10 to the 24th. And you divide all of that by little r, which is 6.74 times 10 to the 6. Let's say you did this. You plug this into the calculator carefully, and you get 7,686 meters per second. By the way, if you go on Google, and you look up International Space Station, you're going to see that the velocity is really, really close to this number, right? The actual velocity is really, really close to this number. Obviously, there's always some small variations here and there. Okay, that's part A. Let's do part B. I don't have a lot of space here, but I don't need a lot of space. This should be enough. For part B, I'm looking for the period, orbital period. So what is T-sat? And remember, there's two ways I can do this. I can use this big equation up here, or the bright green equation, the smaller one. You should always try to use the smaller one, obviously. And I know V, so that's what we're going to do. T equals 2 pi r over V. So it's 2 pi. R is going to be this number down here, 6.74 times 10 to the 6. And V is 7,686. Once you do all of this, you get 5510 seconds, which I went ahead and converted to hours just to get a better idea. You don't have to do this unless the problem tells you to, but a lot of problems will tell you to do this because they want you to kind of make sense of what's going on. 1.53 hours, okay? So this means that the period of the International Space Station is 1.5 hours, 1.5 hours, which means that every hour and a half, the space station actually makes a full circle around the Earth, right? So if you could see it, you would be able to see it going by several times. Pretty cool. Then parts C, D, and E are conceptual questions. And it says, what would happen if it was slightly faster or slightly slower? Remember, this velocity here is the velocity to have circular motion, to have circular orbit. And let me go back here and write this here. Okay, this is the velocity you need to have circular orbit. And let me go up a little more. And I told you that there's a magic velocity at which this happens. And now we know that this magic velocity here is the square root of gm over r. Okay, that's this guy here. That's what's needed. Okay. So that number means you're in perfect circular orbit. But remember what I told you. If you're slightly slower than that or slightly faster than that, what happens is that you're, instead of having a perfectly circular orbit, you're going to have an elliptical orbit. Now, the farther you are from this number, the more elliptical it's going to be, the more stretched out of a circle it's going to be. And the closer you are to that number, the more of a circle you're going to be. So you don't really have to be perfectly at that number. You just have to be close so that you have a very close to a perfect orbit, circular orbit, okay? What happens if it's much faster? Well, if you look at the diagram on top of the page, if your speed is much, much faster than that, then you're going to escape the Earth. Okay, the Earth won't be able to pull on you hard enough. You escape the Earth. And what if it's much, much slower? Then you're going to fall into the Earth. And that sounds like bad news. In fact, that's how they get rid of satellites when the satellite doesn't work anymore or whatever, or they want to maintain it anymore. They might just leave it spinning around the Earth. They could try to accelerate it and shoot it away from the Earth. But very often these things sort of run out, right? And they start getting slower and slower because up there's a little bit of friction, very tiny amounts. And it's going to eventually start falling to the Earth. And these things take days and days, sometimes even longer than that, spinning around the Earth until they splash somewhere, hopefully in the water and not on top of a city or something. Okay, so I want to make one last point here. And astronauts in the International Space Station are not weightless, right? So there's this misperception. It's a big conceptual point in physics. There's this perception that if you're in space, you're just floating around because you're weightless. Weightless means your weight equals 0, which means weight is mg, which would mean that the gravity at that point is 0, and that's not true, okay? In fact, the reason why they look the way they do is because you're constantly falling. So imagine that you're just falling the whole time, right? Except they get used to it, so they're not yelling anymore, and they get used to that feeling. If you were in an airplane and the airplane were to free fall, and then you were to free fall in a controlled manner with it, it would look like this, right? You'd just be floating inside of the airplane. You'd be able to sort of air swim everywhere. In fact, they have that now. You can do that. It's just cost a bunch of money, okay? So they're not weightless. They're constantly falling towards the Earth, but they're inside of the as they spin around as well. But they're inside of the satellite or whatever, or the International Space Station. So they're falling together with this thing around the Earth. So it looks like they're just floating there, which they are. They're falling and floating, but they are not weightless. That effect when you're falling with something, so it looks like you're flying. Also that it looks like you're weightless. It's called apparent weightlessness. Apparent weightlessness. But there is no such thing as weightlessness unless you were to go really far away from any objects, really, really far from any planets or stars or anything like that, then maybe you would be able to get away from all these forces having any impact on you. And then it says here, in fact, the acceleration there is 8.7. So the acceleration on Earth is 9.8. And if you go all the way up to the International Space Station, the gravitational acceleration is actually fairly close to 9.8. It's 8.7. They're experiencing something similar. It just feels different. Another reason why it feels different is that they're inside of this space station, so there's no air resistance. If you were to jump, let's say you're skydiving, whatever, as you're falling, there's just all this air in your face, so it feels like you're falling, right? That's the normal sort of feeling of falling that we think of. But when you're out and there's no air resistance, you're literally floating in the air. But you are not weightless, okay? You're not weightless. There is gravitation, there is gravity on you, all right? So this is also referred to as zero gravity, but that's, again, wrong. It's just apparent weightlessness, or, zero gravity with quotations around it, because there's actually gravity. Cool. So just a quick conceptual point there to wrap it up. Let me know if you guys have any questions, and that's it.